In this problem, we have a pendulum that is starting at rest, and we are looking for the angular velocity, which is omega, at the bottom of the swing. The theta given is 30 degrees in the vertical. The length of the pendulum is 30 centimeters with a mass of 300 grams. The pendulum here behaves like a thin rod. Since we are going from a height to a lower height, the best way to solve this is the conservation of energy. So the conservation of energy states that energy initial, must equal energy final. The two main types of energy possible here is potential energy and rotational kinetic energy. There is a potential energy final possible and kinetic energy rotational final. We know that the initial rotational energy is going to be 0 because it's starting at rest. We know the final potential energy is going to be 0 because we want the velocity, the angular velocity, at the bottom of the swing. So my formula becomes mgh equals to 1/2, since it's rotational, I, the moment of inertia, omega squared. The I for a thin rod is 1/3 ml squared. So we know we're looking for omega. We know I. We have to look for h. When the pendulum is vertical, the length of the pendulum is L. When the pendulum makes an angle, theta, to the vertical, the length of the pendulum is L. To determine the height that it falls, I need to make a right triangle, and I have to actually determine this distance to find how much it falls. So this is adjacent to theta, so it is cosine. So this becomes L cosine theta. So when we did the previous pendulum problems, when it was circular motion, the height that it fell was L, this entire length, minus L cosine theta, which was this portion. And this is how we determine the height. It is the same procedure for a thin rod or a pendulum in a rotational motion. However, we don't determine the entire rod. The part that we determine that falls is the center of mass. In a bar, if it's uniform, the center of mass is located in the middle. So the length that is actually going to fall is not L, but L divided by 2. So the height that actually falls, if I rearrange this, it's going to be L, factor it out, 1 minus cosine theta divided by 2, because the center of mass is half the length of the rod. So plugging this in, this becomes mgh, which is L over 2, 1 minus cosine theta. This is equal to 1/2 I, which is 1/3 ml squared times omega squared. Some things can be canceled out. The half here cancels out with the half here. The m is the same, so the masses cancel out. The L on the left cancels out with one of the L's on the right. Now I'm going to rearrange this to solve for omega. So omega is equal to G times 1 minus cosine theta There's a 1/3, so I need to multiply both sides by 3. There's a L that needs to be divided out, so I divide it here, and we take the square root. So if I plug my numbers in, this is 3 times 9.8 meters per second squared. 1 minus cosine 30 divided by L, which is 30 centimeters, converted into meters to be in SI units. Take the square root, which equals to 3.623 rads per, or radians per second. So, to find the angular velocity of a pendulum at the bottom of the swing, since it's rotating, you will have rotational kinetic energy and no translational kinetic energy in this problem. All the potential energy at the beginning will be converted into rotational kinetic energy. You can determine the height that the pendulum or the thin rod falls, just like when we solve for circular motion of pendulums. So the length is L, make a right triangle, find the vertical length, subtract from the original length to get L minus L cosine theta. Since we are dealing with rotational motion, it is not the entire rod that falls. The reference point in which we measure the fall is from the center of mass. Since the rod center of mass is halfway, your L minus L cosine theta is divided by 2. So here we have a 0.8 meter long uniform rod that is free to rotate. It's hanging vertically straight down, and at the bottom it has a linear speed of V0. So what the picture looks like is we have a pivot point right here, and the rod is held vertically down. It is going to the right at a speed of V0. This is our linear speed, or the tangential speed. This rod is going to rotate, and when it rotates, it's going to look like this second picture right here. So the bottom part is going to be at the top. At the top of its swing, at the straight up orientation, it's going to be there for a moment. Since this is rotational motion, my omega is going to be 0 rads per second for just a moment. So if I draw the two entire pictures together, this is what it looks like. Down here is the bottom of the swing. Up here is the top of the swing. So we know there's a height difference and there's energy. Since there is no friction or air resistance, this is a conservation of energy. We know that E initial, energy initial, must equal to energy final. Two possible energies are potential energy and kinetic energy rotational. Potential energy final plus kinetic energy rotational final. My initial potential energy is going to be 0 because I'm going to set my 0 at the bottom cm. Remember, for a rod, we measure everything from the center of mass. So I'm going to make this my 0 point. So that's going to be 0. I'm going to have kinetic energy rotational because it has a linear velocity. At the end, we're going to have potential energy final because it goes up a height, but we will have no rotational kinetic energy because at the straight up orientation for a moment, therefore my omega is equal to 0. Since this is a thin rod, I know I is equal to 1/3 m L squared. I also know that since linear speed is given, or tangential velocity, this is equal to r omega, and r here, if you notice, is going to be the length omega, because from the height is from the center of mass to the center of mass, and that is the same thing as the length of the rod. So rotational energy is 1/2 I omega squared. This is equal to mgh. So 1/2 I is 1/3 mass times length of the rod. Omega, if I substitute in, will be V over L squared equals to mgl. So the masses cancel out because it's the same on both sides. We have a L square on top. We have a L square on the bottom, so that cancels out. If I simplify the math a little bit, this is 1/6 velocity squared is equal to gravity times L. So we're looking for velocity. So if I rearrange this, 6gl square root, or 6 times 9.8 meters per second squared, times the length, which is 0.8 meters, square root, equals to 6.86 meters per second. So the minimum velocity that it needs is 6.86 meters per second. Remember, everything for a rod, the distance that it falls, or the height, is measured from the center of mass. If we have a height difference and the object is spinning or rotating, you will have potential and kinetic energy rotational.